Given an array where each element represents the height of a potential side of a 2D container, and each side is 1 unit away from adjacent sides, return the maximum amount of water that can be stored by choosing 2 sides to make the container. Now this can be a little confusing to understand, so let's visualize this. Let's say the array at the top is our given heights array. If we drew this out, it would look something like this. The value of each element is the height of each vertical bar, and the index represents its horizontal position. So for example, if we pick the first and third sides to form the container, we would be able to fill it up with this much water. Now the question is, what is the area of that blue rectangle? Well, the height of the rectangle is 1, and the width is 2, so the area is 1 times 2, which is 2. Now notice that even though this side has a height of 2, the height of the rectangle is only 1, because it's being limited by the shorter side. This concept is going to be very important when we figure out how to solve this problem optimally. The height of the rectangle filled with water is always bounded by the shorter side. We could also pick these 2 sides, and now the rectangle has a width of 2 and a height of 5, so the area is 10. And again, the height of the rectangle is bounded by the shorter side of 5. Now one way to solve this is just to calculate the areas of every possible combination of sides. So we'll start by making the left side 2. If the right side was 6, then the container would have a width of 1 and a height of 2, so the area would be 2. If the right side was 1, then now the width is 2, but the height becomes 1, so the area is also 2. And we'll continue this for the rest of the row. Now let's make the left side 6, and we would start by making the right side 1. This container would have a width of 1 and a height of 1, so the area is just 1. And again, we'll continue this logic for this row and fill out the rest of the table. And now looking at our results, we can see that the greatest area turns out to be 12. Now this approach works, but the problem is that this algorithm runs in O of n squared time. If you're not sure why that is, skip to the end of the video and I'll explain why. But there is a way to solve this in O of n time, and the key is to get rid of all unnecessary calculations. But how do we know which ones are unnecessary? Well, the strategy here is to start with a container of the longest width, and then see if we can get a bigger area by shortening the width but finding a greater height. So the container with the longest width will be this one, with a width of 4 and a height of 2, so the area will be 8. Now the question is, which side should we move inwards to get a new container? Well, if we decide to move the taller side of 4, so now the right side is 5, notice that the height of the water didn't change, even though the height of the right side increased. And this is because, like we mentioned earlier, the height of the water is being limited by the shorter side of 2. So by moving the taller side, the height of the water will only either stay the same or get shorter. This leads us to a very important conclusion. We will never be able to get a larger area of water by moving the taller side, because the height of the water cannot be increased and the width will keep decreasing. That means we don't need to do any more calculations with the shorter side of 2, and so we'll update our container by moving the shorter side. So let's move the left side so that it's now 6, and we have our new container of water. The width is now 3, and the height is 4, so the area is 12. Now again, it's pointless to change the taller side of 6, because the height of the water will only either get lower or stay the same. So we can skip all those calculations, and instead, we'll move the shorter side of 4 to be 5. The width is now 2, and the height is 5, so the area is 10. And for the last iteration, again, the shorter side is 5, so we'll move that inwards and calculate the last area, which has a height of 1 and a width of 1, so the area is just 1. Now we can't move the sides of the containers inwards anymore, so we are done. Now when we look at the results, we see that 12 is in fact the largest area of water possible, but notice how this time, we only needed to calculate the area 4 times, or n-1 times. So the algorithm now runs in O of n time. Now let's look at the code and see how we can implement this in Python. First we'll define a variable called max area and set it to 0. This will hold the maximum area of water. Then we'll create 2 pointers. L will point to the leftmost element in the array, and R will point to the rightmost element in the array. Note here that L and R are actually array indices, not the elements themselves. Then we'll iterate as long as the left index is less than the right index. The first thing to do is calculate the area formed by making L and R the sides of the container. R minus L is going to be the width of the container, and the height will be the minimum of the 2 sides. So 4 minus 0 is 4, and the height of the shorter side is 2, so the area will be 4 times 2, which equals 8. Then we'll take the maximum of max area and the area we just calculated, so that max area always contains the largest area encountered so far. Right now, max area is just 0, so we'll update it to be 8. Now we compare the two sides, and remember, all we have to do is move the shorter side inwards. The left side is shorter here, so we'll increment L. Then we'll do it again. R minus L is 3, and the shorter height is 4, so the area is 12. 12 is greater than 8, so now max area becomes 12. Now this time, 4 is the shorter height, so we'll decrement R. Now R minus L is 2, and the shorter height is 5, so the area is 10. 10 is not greater than 12, so we'll keep max area as 12. Now 5 is the shorter side, so we'll decrement R again. Now the width is 1, and the shorter height is 1, so the area is also 1, which is clearly not greater than 12, so max area stays the same. The right side of 1 is the shorter side, so we'll decrement R, but now notice that L is equal to R. That makes the loop condition false, so we'll exit the loop and return max area, which is 12, and we're done. We have solved the problem in O of n time. Now, going back to why the first solution was O of n squared, if the length of the array is n, then the first iteration took n minus 1 steps. The second iteration took n minus 2 steps, and so on until we reach 1 for the last iteration. So how many steps is that total? We can use this formula here that tells us that the sum from 1 to n is n times n plus 1 over 2, or n squared plus n over 2. So to find the sum to n minus 1, let's take n squared plus n over 2 and just subtract n from it. After a bit of manipulation, we can see that this ends up being n squared minus n over 2. And since with big O notation, we only take the dominant term and drop constants, this ends up being O of n squared.